The VSEPR theory is a synopsis of how all these different shapes that we've been drawing result in an overall image. So remember, electrons are negative. So what they're going to do is the electrons in this bond and the electrons in this lone pair, they're all going to repel each other as far away as possible. So the number of bonds and the number of lone pairs that a molecule has is ultimately going to change its geometry. If I added extra electrons, I would bend everything even farther away. If I took electrons away, it means things could get not bend things farther away. It means that it would reduce the angle between them. And if I take electrons away, everything can spread out more. So for example, if we're looking at the difference between, we'll use ammonia as our example. Ammonia has that lone pair, H, H, H. Okay, in reality, there is about 109.5 degree angle between all of these because there has to be an angle between here, between here, between here, and between here. And it's three-dimensional. So you have to imagine that this is on the XYZ plane. If I get rid of the lone pair and we just pretend like nitrogen can exist this way, with only 3 electron sets, the farthest away they can be from each other would be 120 degrees. So the geometry would be completely different. The 12 shapes that you have to know are based on how many bonds are attached to all the central atom, as well as how many lone pairs are on the central atom. So use the chart that you have in your textbook or on in your reference sheet, and you just got to memorize them. So get going. If we're drawing larger molecules, basically the rules still say the same. The element that's written first tends to be central, so we're going to put 2 C's in the middle. And then the one that's written second tends to be surrounding the outside. So I'm going to put my H's evenly placed like this. Okay, and then, oh, that doesn't look like an H, hang on. Beep. If I'm using what I've learned, I add up all of my electrons and I just start attaching things. So 2, 4, 6, 8, 10, 12, 14. Wow, amazing. Look at how that worked out. No way. So basically what we're looking at here is 2 tetrahedral shapes attached. So even though this is a large molecule, those 12 VSEPR shapes are still going to pop up around every atom that you could consider central. So even if we're looking at something like this, okay, this is a really large molecule, its overall shape is very complicated, but the individual shapes, you would just zoom in on one atom and make a decision about that atom. So for example, here's a carbon that has a single attachment to an H, a double bond attachment to a C, and a single bond attachment to another C. No lone pairs because we know carbon can only have 8 electrons touching it. So this would be a trigonal planar shape, which means that I can also make an assessment that there would be a 120 degree angle between the elements that are surrounding it because I know that that's the angle that goes with being trigonal planar. If we're comparing it to, say, this sulfur right here, what we need to remember about sulfur is it needs to have the octet roll finished. So what's missing from this image is 2 lone pairs that they just didn't feel like adding. So I know from memorizing the chart that 2 single bonds and 2 lone pairs make my molecule bent, which means that the angle between these 2 carbons right here would be 109.5. And last but not least, let's say I'm looking at, oh, I can do a couple more actually. This one, okay, even though they didn't spread the carbons out, okay, we know that hydrogen's attached to carbon this way, and the other attachment is to this C. Okay, this would be what we would consider tetrahedral. So tetra, I'm not writing very well, but you get it. Tetra, which means 109.5 would be the expected angles. And then let's do this one. Okay, what's missing here? A lone pair. So I know that 1 lone pair and 3 single bonds makes that a trigonal pyramidal, which means 109.5 would be the bond angles. And the only other thing that I can think you might be asked is to compare like this bond to this bond. So remember that single bonds are longer and weaker. double bonds are shorter and stronger. So if you had like this bond listed as A in a multiple choice and you had this bond listed at B, and it said which of the following would require more energy to break, the answer would definitely be B, because a double bond is always stronger than a single bond.